So, welcome to our last session today before we go to the boats tour. And that will be another highlight. I'm very, very happy that we managed that Irina Rish is here today with us. As you can see, she is at the University of Montreal. She's a full professor there, and she's also with Mida. In addition, she holds a Canada Excellence Research Chair in Autonomous AI and a Canadian Institute of Advanced Research, CIFA, AI Chair too. In addition, she also is involved with her own startup. She's doing a lot of things, actually. She works on foundation models and many, many more things. And I think we have seen it already this week quite a bit, how important that research direction it is. And I'm even more glad that she's here today and can tell us much more about it, that we have more insight and knowing much better how we can connect and how we can contribute to that. So a big round of applause for Irina.
Thank you. Yeah, thank you so much for inviting me. I'm actually really happy I made it. That was, yeah, a few hiccups. And I apologize for my voice. Yeah, kind of getting better today, but yeah, it's not like I'm a heavy smoker. It's just I had a cold. So yeah, indeed. Yeah, as you were saying, the most recent kind of directions in the lab are mostly focused on scaling laws, foundation models, large-scale models, various applications of those, various modalities. I'll talk about that. I'll talk a little bit about history of scaling, but it is in a sense complementary topic to the topic of this conference, because doing AutoML, doing hyperparameter optimization at scale is particularly hard, if not impossible. So whatever people usually do at regular scales will not work at extremely large scale. Like you cannot do your grid search of hyperparameters or anything. So the question of extrapolating, predicting behavior and from smaller scale to larger scale will be a big open question. And anything along those lines that can help like people in foundation model field optimize architectures, optimize parameters, and in any case, kind of automate ways foundation models are created. Yeah, so that's a big open challenge. So I will pretty much kind of present like what we are doing, what's in the field, and I invite everyone to brainstorm later on like how the AutoML can scale. And I think it will have to, in the given the kind of foundation model revolution that's happening. So yeah, going back to where we all started, and the previous talk, previous plenary also mentions kind of all about generalization in a sense. So essentially the holy grail of AI was always generalization, starting from good old statistics, fitting curves, generalizing to unseen points from the same distribution, then multivariate machine learning methods kind of trying to do the same within hopefully distribution of training data. Then people really wanted to go out of distribution, further and further out of distribution, meta learning, continual learning. The goal is to essentially try to train systems that somehow will manage to expand their kind of performance to further and further from the training data type of new data and tasks. And for all practical purposes, you don't have to kind of treat AGI as something mysterious or whatever, although there is lots of controversy, like you better don't mention that term, especially on Twitter. But for all practical purposes, it's artificial general intelligence. It's a very capable system, or maybe collection of systems that can truly generalize very far away from kind of what it's seen so far. And it's useful. So kind of OpenAI definition, vague, but on point. Anyway, so this Canada Excellence Research Chair program at, again, very high level, started like back in 2020. And the high level goal was, okay, how do we push AI towards more broad from narrow specialists, because those days things were indeed much narrower than what we see now. And how do we kind of make them less human dependent? And that was a goal. So lots of work in our lab started with and actually continues right now on the topics of, say, continual learning and out-of-distribution generalization. I'll just briefly go over a few things. There's much more that I will not going to cover, but just to give you an idea, it's perhaps one of the most challenging types of out-of-distribution generalization problem, because it also happens in time when standard machine learning considers data distribution, samples from it, and tries to fit whatever model to that. Here you have a sequence of such data sets, and you want to ideally build one model to rule them all. The model has to keep adapting without forgetting what it learned before. So at any point, you can take the model and test it on kind of problems from all the previous, say, data sets. So challenge is it happens in time, and you don't necessarily have everything that you've seen so far in memory. So you need to somehow avoid forgetting. And applications are many. I mean, this is just one example where, for example, you build a system for some medical diagnosis, like say medical imaging, and you really would like the system to also adapt and generalize and work well in other hospital. You don't want the machine, basically deep learning, to latch on some spuriously correlated features of medical imaging that have nothing to do with disorder, as deep learning kind of was known to do. You wanted to truly learn like invariant features. So it's the same kind of goals of like invariant risk minimization and other kind of topics in out-of-distribution generalization. In continual learning, it becomes particularly challenging. And even more challenging domain that we kind of were looking into and doing some work in, and this is kind of a survey on kind of state of art in continual reinforcement learning, where things get most challenging than in just a standard supervised or unsupervised machine learning, because you truly have changes in the environment, and you have changes due to behavior of other agents, and you really want very flexible agent that can kind of take this into account and keep learning continually. Anyway, it's just I'm giving very high level overview of type of domains and problems that we were looking into, and which are very hot topics and been there for quite a few years, like past 5 years at least. But if you think about that, out of distribution generalization proper, or domain adaptation, or meta learning, which is continual learning, transfer learning, all of that, it's about future and further generalization. And then 2020, GPT-3 is released, and the first neural scaling laws papers appear. I'll talk about that in a moment. And the claim to fame of GPT-3 is now this so-called, well, called later, year later, foundation model. Back then, they didn't call it yet. It can generalize with very few shots or samples to totally new, unseen tasks and domains that it was not necessarily trained on. It's trained in an unsupervised way. So it doesn't know what task you want to use it for. And it generalizes. So this was like a jump in generalization. And the question was, okay, so maybe these models that seem to be mainly differing from the previous state of art by their scale, not really new algorithms or new architectures, maybe that scale does something magical to generalization. And the question is why? And of course, a year later, in August 2021, there was a very comprehensive white paper from Stanford, led by Purcell Young and collaborators, that coined the term foundation models, saying, okay, those unsupervised models pre-trained on large and very diverse amounts of data, they're like a foundation because you still kind of, you can build on top of them particular applications, but they're also not kind of complete. They require some fine-tuning, they require maybe some adaptation and alignment and so on and so forth. So they call them foundation models, but essentially it's a model pre-trained without any specific goal in mind, just doing autoregressive tasks, next token prediction, whether it's language or images or time series more recently. I will mention that, one of our projects, and essentially just learns about the world, how it is, how language works. And then apparently, if you learn that from sufficiently large and diverse set of distributions, one hypothesis could be that why foundation models work. Or maybe compositional generalization. Like think about doing a simple, I don't know, SVD or PCA on huge dimensional space. If you sample properly from that space, diverse enough set of data, and if you assume that your data, your world is such that it's well approximated by finite number of PCA components, then at some point, if you manage to get diverse enough data, you'll find those components. And after that, you should generalize by recombining them to many, many things. Of course, this is not linear space. It's not necessarily, I mean, it's not a linear kind of problem. It's not linear autoencoder problem. But the analogy may hold that if you train model on sufficiently diverse data and it kind of grasps the quote unquote principal components of how language works, how images work, and so on and so forth, then maybe it can just recombine them and generalize. And it seems maybe something like that is indeed happening. And of course, yeah, so that's a famous good old GPT-3 claim that nothing changed except for scale. Same good old autoregressive model, same good old objective, nothing changed with optimization, and nothing changed with architecture. Scale changed, and that changed the results. And then, of course, fast forward, all the recent Cambrian explosion of foundation models, language, images, audio, coding, you name it. And yeah, GPT-4o right now, yeah, some of my students spending hours a day talking to it about all aspects of their lives. And actually, they find it much more useful than talking to people. Well, go figure. So what's going on? Comes to mind, probably some of you have seen that. Back in 2019, Rich Sutton wrote this short blog about this bitter lesson. It was actually before GPT-3, but it was exactly the point, that if you look at the whole history of artificial intelligence in the past 50 plus years, what's the trend? The trend is clearly automation. People started with rule-based systems, right? And then machine learning was learning those rules automatically. But people had to spend a lot of time on basically extracting domain-specific good features in images, in audio, like speech, in language. And there were so many papers published about that. And then deep learning came, again, the trend with increasing compute and increasing data, the models becoming somewhat more generic, and they replace or automate this work that people had to do by hand. And then the story, of course, goes on that some specific architectures become replaced by more generic sequence kind of handling transformers, that all kind of ontologies used to play chess replaced by massive search. So the trend seems to continue that with increasing amount of compute and available data, we have more and more automation using methods that are sufficiently generic and scalable, and not necessarily too overfit or full of constraints and inductive biases. And the bitter lesson is that you may try to overcomplicate your approach, and it will help you win in the current relatively small scale environment. But this paper will not probably win, I don't know, test of time award, because it might be replaced by something dumb and generic, which scales. So something to keep in mind. And that was a classical example from old paper on the vision transformers, where essentially if you compare convolutional networks to vision transformers, of course, on relatively small amounts of data closer to the left, convolutional networks rule, they were state of art always and so on. But if you keep giving more and more data, then this inductive bias with convolutions may become somewhat constraining. And transformers, which are somewhat dumber or more generic without any specific biases of that kind, they seem to be able to grasp data distribution better. So in a sense, like it's very Bayesian. Like if you don't have much data, you need smart prior. But if you have more and more data, hopefully your model is generic enough and not too constrained, so it will let the data speak for itself. Apparently, transformers did that. And the situation reverses. And when you look at that, you basically say that historically in machine learning, how do we compare methods? Almost always you have comparison for particular benchmarks of particular size. You have comparison for particular architectures, particular size. And this seemed to be so deep-seated in our minds. And even like younger students are still in that kind of part of the mental space. While you keep telling them that don't be bitter lessened, compare whatever you propose or whatever other proposed in terms of trends, how the trends will look. At least you know what works best for small versus large scale and the medium scale. So trends, or basically like investment tools in machine learning methods, I think we all should be evaluating whatever thing in terms of how things compare when data grow, compute grows, and model size grows, at least. So at least you know what works best when. So point comparison may be really giving very limited picture. So yeah, I promised to also talk quickly so we don't have to sit here until 6. And I will just mention very briefly, so kind of motivated by this idea of working on the scaling laws and investment tools and so on, we were exploring in the past couple of years several approaches, like how do you predict behaviors of your systems, well, performance, but not only, there are many other metrics, people in alignment and safety interested in, robustness and so on and so forth. So basically whatever the metric is, how can you go about predicting it? And one approach is like closed box or scaling laws, where all you see is behavior of the system, or you look at papers and all you see is scaling results. You're trying to see whether you can fit and extrapolate some scaling law. And the second, if it's actually your system and you can see learning dynamics, maybe you can look for patterns that will be predictive. And I very briefly give a few examples of both approaches. So the first approach led to this famous paper by Jared Kaplan, again in 2020, where it was observed purely empirically that at very kind of large scale, multiple orders of magnitude and massive experiments, because it was kind of during training GPT-3, you do observe this, well, classical picture that many of you probably know by now. You see that performance, like in terms of like test loss in this case. And that's important because test loss behaves sometimes quite differently from the metrics and performance on specific downstream tasks. But at least for test loss, quite often you see those power laws or straight lines on log-log plot, which essentially mean that for any fixed quantity on x-axis, say you fix compute, and try to find the model size and data that kind of performs best at that amount of compute, you will see that the best performance, like loss, will go down according to power law. And similarly, you see that when data set size increases and parameters. So there's famous straight lines, which are observed not just for transformers. Apparently, it kind of applies even to good old multi-layer perceptrons. So they also scale, perhaps not as efficiently as other architectures, but it kind of makes you think that if you have infinite compute, maybe, yeah, if it doesn't cost you anything, why not scale MLPs? At least it's good to keep it in mind. And then you actually start looking like, okay, people of course looked into that, but just didn't have maybe enough compute to really observe at multiple orders of magnitude what will happen. Actually, the very first scaling laws paper that we could find dates back to 1994 by Karina Cortes, Vladimir Vapnik, and collaborators. And it was NeurIPS, well, back then NIPS 94 paper, where they actually observed that with amount of data on x-axis, in that case, it was log of error of simple neural network, I think 2 layers or something, follows power law. So I think that was the first straight line on log-log plot. And then there was lots of subsequent work, even before Jared Kaplan. There was work by Joel Hasnes expanding this to order of magnitude. There was work by Jonathan Rosenfeld, 2019, showing that same type of power law holds for X being model size, not just data. And then Jared Kaplan combined that and kind of also kind of confirmed these observations plus compute scaling law in very large scale experiment of like training GPT-3. So it's been an interesting kind of history of scaling laws. Then there are some recent refinements, not so recent anymore, like a few years ago, that show that actually scaling law with compute that was in the original Jared Kaplan's paper can be improved. And actually, if you invest, given certain amount of compute, not more in the model size versus data, like that paper suggested, but actually 50-50, there is a chinchilla scaling law, you can actually get better performance with smaller models. And that's been like a recent trend. Probably should just skip that. Probably many of you have seen those papers already, both chinchilla and then follow up Llama 2, Llama 3. Bottom line is models become smaller, data become larger. And so far, this trend, while following chinchilla scaling law, or even going beyond that, saying if you don't mind being not compute optimal, but kind of waste some compute, you can get even better performance at even smaller model scale, but with larger data. So that was kind of the good old Llama 2, which showed that despite training even the smallest model on like this 2000 billion tokens, basically trillions of tokens, it still doesn't show any sign of saturation. So while this was all interesting and power laws were kind of guiding various choices, like what was good about scaling laws, like say you have choice of hyperparameters, architectures, or any kind of decisions regarding design of your model, if you can quickly estimate scaling law, it helps you choose things. So in this case, scaling laws are very natural potential tool for AutoML. Of course, I mean, it might be expensive tool as well, because in order to compute scaling law, you need to have a few points to get the trend. But in principle, that apparently was a way during the GPT-3 kind of training, how different architectural decisions were selected or not selected. But the interesting thing is these power laws, as I mentioned, mainly apply to test laws. When you start looking into downstream tasks, you start seeing very unusual behaviors, but now they're quite usual. But when the first time on the right in the GPT-3 paper, on a particular downstream task of arithmetic, like 2-digit or 3-digit or 4-digit, people observed that actually it's not anything like power law. Here there is certain emergence or transition or sharp change in behavior, depending on model size and complexity of the problem. Like the harder the arithmetic problem, the later kind of GPT was starting to understand how to do that, and larger model size was needed. So it was one of the first kind of observations of these transitions. Then there was a Groking paper like in the middle. And that was, again, an interesting anecdote. Was iClear 2021 workshop paper where literally on the arithmetic model or something, they tried to train model, and the model was just not generalizing at all for a long time. And apparently the story goes, they forgot to kill the run. And then when they look at the results, they saw this, that at some point after not working for a long time, it first memorized red line. So basically started working well on test data. And then after a long while, same thing happened with generalization. So it grokked the problem, but it did it relatively unexpectedly, transition-wise. Then there were papers, of course, of emergent behaviors in language models, follow-up papers showing that, of course, depending on metric and depending on the downstream task, these nonlinear sharp changes are happening. There were also papers like by Rylan Sheffer that maybe it's just a property of metric you use, but the answer is there is more evidence it's not just property of metric, and it may also happen with a loss. It depends on the problem, downstream task, and the answer is it depends, but yes, sometimes you have nonlinear sharp transitions, and understanding them to predict what's going to happen is extremely important, whether it is for knowing which method will perform better, whether it's for knowing whether this run will end up in grokking, or if not, maybe you drop it and choose other initialization, other parameters, or for safety reasons, because if y-axis is robustness, truthfulness, or anything related to safety and alignment, you would like to know if there are going to be any sharp transition in some future in that metric. So that kind of led to all this exploration of so-called open box predictions. And it's not just us, it's many other groups by now who looked into this grokking and related kind of problems. And yeah, so it was a grokking problem. And let me just skip to the interesting result. Purely empirical result, like one example of what you might be looking for, say, if you, in all the empirical results that were kind of obtained by the lead student, Pascal, on this paper, essentially whenever grokking would happen, he would see high frequency oscillations in both training and test loss. And if he didn't see those, he didn't see any grokking, no matter how long he would run. I mean, there is no guarantee it never would happen, but it kind of, in terms of selecting good initialization, like if you keep running, you don't see those, you say, maybe I should just restart. So this is example of a pattern you might be finding predictive about, say, things like grokking behavior. There are many more. I'm not going to go into that. There is lots of work, of course, now on this type of understanding grokking, like tons of papers from several places in MIT and Berkeley and so on. It's very interesting, and it's still open question to fully understand what happens when. But switching to now kind of closed box, okay, if it wasn't our system and we couldn't run it and we wanted scaling laws that would generalize or extend usual power laws to those non-linearities, to sharp transitions, what could we use? And another student of mine, like Ethan, he looked into that problem and was searching for what kind of functional form could be replacement for simple power laws. And apparently, like, well, look at physics literature, especially astrophysics, people use so-called broken power laws or smoothly broken power laws, where you have several regimes, and in every regime you have power law, but the connections between those are smooth, but could be sufficiently kind of steep. How steep, when they happen, and so on, are all parameters of that functional form that need to be estimated from data. But the interesting thing, again, it's purely empirical work, but it's quite impressive that no matter what set of scaling results in various papers in the past 3-4 years he looked at, he always could fit and extrapolate using one of the functions from that family with proper parameters. So essentially, it looked like a very generic form, functional form, to cover all those unusual or non-linear cases that not only power laws could not cover, there were some more recent approaches that try to kind of model non-linear behaviors, also non-monotonic behaviors and so on. So basically, yeah, it was quite interesting and seems to be a very useful empirical thing. Like if you want to fit power laws and you are not, things do not look totally linear, the smoothly broken power law seems to handle whatever modalities, whatever type of task, architecture, so anything. So generic enough. And even if the stars align, you might be able to predict upcoming transition. But again, if the stars align, which means it's simulated experiment where you don't have much noise, you're close enough to the transition is not too sharp. Of course, if you really want to predict transitions, you probably need to combine methods like that with open box looking into patterns of training dynamics. But in any case, it seems to be like a useful modeling tool for predicting non-standard, non-linear behaviors. Now, switching gears, and I think I don't have that much time left. How do we, in practice, not just kind of study scaling laws, like can we build those models? And the challenge was always that, well, in academia, you don't have much compute, so what do you do? So compute is concentrated in a few companies, and compute is expensive and so on and so forth. But apparently, there are publicly available, multiple supercomputers of different size in different countries. By now, I think they're being widely used, but back then in 2021, 2022, we were kind of just discovering these opportunities for ourselves, although colleagues in physics and I guess biology and chemistry and neuroscience were using those large-scale supercomputers for quite a while for large-scale scientific simulations and other things. Just AI people were not applying for those. So we did apply with a large collaboration of friends, including some German friends in Lion and many others. And we got those allocations on Summit supercomputer, then Frontier, which going to replace Summit. They both in the US, and they kind of, Frontier at this point is largest, I mean, the fastest, basically top public supercomputer. Of course, we are not talking about the proprietary clusters and companies, but for kind of public scientific purposes, that's seem to be the top in the world right now. And you can apply using like collaborative applications for some large projects, or you can apply for smaller ones. There are director discretion allocations, and you can get some compute, although of course you need to adjust how to train things on specifically those architectures. But Frontier is, for all practical purposes, very generic. Even though it's AMD, you do not notice that it is AMD, like all fairly standard. And as I said, there was large collaboration over multiple years. Like we started with Lion, Ulis Supercomputing Center, and the Luther. And then there were people involved from Stanford and Together AI and so on and so forth. And essentially it was like University of Montreal and Mila working with various people at various times. And then essentially, well, it's very incomplete list of projects and very incomplete set of team members who worked on those projects. But just to give you flavor of what kind of things we were able to do with medium-sized foundation models, I would say up to like 10 billion parameters. With language models, yeah, last year we released a suite of continually trained ones, again, up to 10 billion. With multimodal, like vision language models, there was this Robin suite and novel evaluation benchmarks for that. More recent thing is time series transformers that seem to be like going beyond the usual modalities of language or images or even audio. It's like arbitrary time series. The interesting things are most recent work trained on basically a suite of models trained on Summit. It's actually using ternary models, and we show that, I'll briefly show a plot, that it's the best trade-off so far that we've seen between performance and compactness or bit size, and well, think edge devices and stuff. So even if you train a full precision model, well, of course, it's not going to have good trade-off in terms of bit size versus performance. If you compare it with quantized models in standard way, they're better. But if you train model that's, say, in linear layers has only 3 values per weight, it's much, much better. I'll show a picture in terms of the trade-off. Interestingly, binary models are not well performing, so it's kind of the middle ground. Anyway, there are like lots of specific details. I'd be happy to discuss if people are interested in particular projects, but I guess offline or on the boat. There are many other things happening, and alignment-related work and some psychological testing of LLMs in that category and so on and so forth. But basically, a few highlights, like last year, together with Stanford and, well, together, essentially on Summit, there was this red pajama data set and red pajama model trained, the 7B that was kind of catching up with Llama 2. That was just Llama at that point in May. It was like one of the first things and released. And then they continued training models released in December, multimodal, as I mentioned, vision language, and test suite, this Robin suite also released in winter. We looked into multimodal alignment and keep looking into that. So things like that will not happen. That's not something that happened with our model, but it's something that used to happen with some older vision language models. Not going to say which one, but can say of like, anyway, so those are very quite primitive and would give such answers. So you would want to of course, gives them some human feedback, even without reinforcement learning. But apparently you give them a few examples of what compassion should mean, because apparently the model didn't quite get it. And you explain what the answer should be. Sample complexity of alignment, at least just empirically, was surprisingly low. I mean, perhaps the smarter is the model, the less hints it may need how to change behavior. But that remains to be an open question and needs to be studied. And I was just kind of giving the flavor of different projects and only very high level what they are about. In February, we released this, essentially it was the first open source time series foundation model, although tiny one, but technically it was the first. And of course, right after that, there are many other time series foundation models appearing, built by Salesforce, like Moirai, by Amazon, Kronos, and so on and so forth. And there's a whole Cambrian explosion, looks like, of time series foundation models now. They were lagging behind language models, well, pun intended, for 3 years. And now they suddenly, it's like a GPT-3 moment for time series. So yeah, we keep actually, it was February. Since then, many things were improved and there is some work in progress. We're hopefully gonna get it out later this fall. The quantized models that I mentioned, that was a plot I was talking about. So again, there was a Spectra suite just released in July on Hugging Face. So you can find a paper there and everything, which includes essentially 54 models of size up to 4 billion, 4 classes, well, usual full precision, or well, FP16, 2 families of quantized, like 3 and 4 bit, in this picture too. And then the bright green one, this tri-LM, is ternary. So apparently figuring out how to train ternary models with specific architecture gives much better trade-off between performance, and the x-axis here is, yeah, you cannot see it, but it is a bit size. Yeah, so I think this window kind of prohibits people from seeing x-axis. So anyway, it's out there. I think it's very exciting. And if anyone wants to build anything on top of those, because pretty much it's like a new suite of language models, they just quantized and efficient. So yeah, you can reach out to me. And the most recent thing, going back to where we started in the beginning, is that remember, like we always were into continual learning. And that continual learning, the classical one, was never using foundation models, and therefore it had lots of forgetting. In the recent years, it was shown in multiple papers that when you start doing learning continually on top of foundation models of whatever flavor, maybe for specific tasks and so on, it definitely has better trade-off between adaptation and forgetting. But despite that, we are not quite on kind of usual basis seem to be training foundation models in continual way, although it seems to be the most natural thing that's happening. Like you have so many models, say, especially in open source, and they're all being built from scratch, and people keep doing that instead of maybe piggybacking on each other's work, right? Or it's your own model and you want to maintain it and new data keep coming. Of course, it is in some sense safer performance-wise if you take all the data so far and new data, mix everything, learn one model. It will be likely a best case scenario in terms of generalization. It's harder to do it sequentially, but it's very impractical. And you cannot keep doing that even if you have infinite compute or whatever of large companies. It just doesn't make sense. So you need to figure out how to keep updating those models. But if you just fine-tune them, they tend to forget, and their performance on previously well-done tasks may suffer. So you want to do the usual continual learning goal of adaptation without forgetting and trying to stay as close as possible to best case scenario. What if you did mix everything? It kind of reminds me about very good old online sparse dictionary learning paper by Julien Mayral and collaborators in like 2008. It was very simplistic setting, but the same goal, although no distribution changes. Like if you have a really huge number of images, instead of learning dictionary, which will be infeasible. You want to do it online, but you want to approximate performance of the dictionary you would have learned hypothetically if everything was mixed. In that case, it was possible theoretically show that you can do that. In case of distribution shifts and transformers instead of linear sparse autoencoders, it might be much harder to do theory, but at least you can try to see what continual learning approaches may be needed so that you can keep training your model without suffering this degradation in performance. And another reason for doing that is like good old, as I said, chinchilla scaling laws and the picture I showed, because you can keep feeding those llamas more food data and they keep improving. But you don't want to do it from scratch. You want to keep doing it whenever the new data set arrives. Anyway, let me skip that. It's essentially, yeah, so that led to this suite of models. And essentially, like a simple example could be like this recent paper in TMLR on simple approaches to continual pre-training, essentially says, okay, what's going on? You can take a model and you get new data. You could just train from scratch on new data. It's kind of lower bound on performance. Or you can mix everything and have the joint training. It's upper bound performance, but it's inefficient. Or you can try to do this continual pre-training. Say we trained model on pile, then switch to Slim Pajama, another data set, or to make distribution shift larger, or switch to actual German. So what happens? And again, I apologize for going so high level, but the gist of the paper and the result is promising. Essentially, the central, I mean, the first plot is kind of obvious. I mean, of course, you save compute if you train continually rather than mixing everything and training from scratch. So it's almost like even shouldn't be there. But the middle one and the rightmost one basically show that if you look at the test loss or you look at the average benchmark performance of the models trained continually, like at different sizes, 10 billion or 4 or 5, and trained continually versus training jointly, essentially it's approximately the same performance. Although on some particular benchmarks, it might be worse, on some others it's better, but on average it's similar, test loss is similar. So it seems empirically you can train sequentially a model that will not be that much worse, that ideal case of the model trained the usual ways of mixing all data, which gives you a hope that you can have maintainable models this way. That's kind of the gist of it. What we did, again, I'm not going to go into all details, but we tried different warm-up schedules. There are a bunch of hyperparameters, of course, which was hard to tune at scale. And that's where I'll talk about that. Any kind of work that can help to generalize those from lower scale to higher scale would be very needed. The warm-up schedule, the learning rate, those were important decisions, and replay. By the way, with learning rate, what worked best apparently was so-called infinite learning rate. So you, instead of doing some usual cosine decay and at the very tiny value of learning rate and then having to rewarm, you can actually do cosine or like it was inverse square root, whatever people proposed in this so-called infinite learning rate. And then you stay at sufficiently high level of learning rate. The question how high it should be for your data and your model is another hyperparameter, of course. So yeah, as usual, but it does allow you to apparently keep training on new data. This model that whenever you actually really need the final version, you can do that exponential decay and get the checkpoint. Yeah, but you kind of keep that warm model forever so you can keep training. So that, again, empirically seemed to be what worked really best. And of course, there was also replay. And yeah, both learning rate schedules with regard to rewarming and particular learning rate schedules and what choices worked better for what model sizes and so on. Replay, just usual classical thing in continual learning, the simplest, but apparently very effective thing of keeping certain percentage of old data and mixing with new data. Reassuring thing was low percentage may be needed to keep up with the ideal kind of model that I mentioned as a baseline. Anyway, it's all in that paper, and that recently came out in HTML. It's purely kind of empirical, but it's more like recipes on how to. And recently there was another continual learning paper for actually the, I think, vision language models that just came out. I also saw it on Lion Discord. Yeah, but bottom line is kind of to conclude, there are so many things happening in foundation models. There are various types, various modalities. People build stuff. People always face a problem with hyperparameters. So it's truly like $1 million questions, literally, maybe not million, maybe billion. Because depending how you choose hyperparameters, your scaling will be quite different. And you cannot do search in any way you used to do on lower scales. So either you do some kind of theoretical extrapolations like Greg Young's μp, but again, it probably has certain, I mean, it's for learning rate, it has some applicability. Yeah, initially it was just for increasing width of network, but now it's also for depth. But what about other hyperparameters, so on and so forth? Empirical scaling laws, perhaps. So you need to figure out maybe algorithms that would quickly do the trend analysis with respect to different hyperparameters. But again, you don't want them to be too computationally expensive. Looking into these internal patterns of training dynamics together with that, perhaps any of the above, probably. So in a sense, it's more like an open challenge to the AutoML community. Like, can we figure out how to do AutoML at really large scale? Because essentially that's where we're all going. And from what I hear from my students who were interns in various companies, it's truly a very painful and important question that is worth definitely millions. So I think it's a good open problem for us to solve in the next few years. Thank you very much.